Okay. Hey, welcome back for part 2. Even though I won't title it as part 2, it's dealing with orbital notations because that's something that they use in chemistry. And in the first part, we looked at the idea of electrons and levels around the nucleus of the atom and how electrons absorb energy, they jump up to other levels, and when they come down, they give off this energy, this emission of energy, and we end up getting something that looks like this. Oh, hey, awesome sauce. Okay, you kind of notice that now this is how the lines are formed on those light emission spectrums, or those fingerprints of light. That's a key thing that I look at here. So this is it. This is what it looks like. All right, now let's get back to, what are you talking about these orbital notations? Well, you know what? I would show you guys that we can do this. And I have worked with this with most of you guys before. And this is a way of placing the electrons, a way of noting where the electrons are going, what level and what sublevel, and, oh my goodness, the sublevel in that area as well. So we're going to be working on that today, ladies and gentlemen. Now, this is related to this, which is ultimately related to this, especially up here. Okay? So, I wanted to show you, which is also connected to this. Can you imagine all that? So, let's go with the basics here. How do we read these orbital notations? Well, there's 3 pieces of information you got to look at. And on here, there is your principal quantum number, or your level number. Then you have the orbital shape, I like to call it the sublevel. And then this magical number here, it's not an exponent, okay? It's just telling us how many electrons are in that orbital. If there's just the letter by itself, then it's just 1. That's it. If there are no electrons in this, then you're not going to see it exist. It's just not going to happen. So 1s2, level 1, sublevel s, we have 2 electrons in there, and then level 2, sublevel p, 4 electrons in there. That's the basic idea. Now you may notice, ooh, hey, there's a certain order that these guys fill in. You're right, 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, and you're thinking, wait, what's going on here? Well, remember, let me go from here to here. Maybe this is going to help you out, okay? The idea is we're writing, how do we write the secret code for electrons in the atom, okay? So let's go, we'll start out with a simple one. Let's start out with hydrogen. Now, hydrogen's got 1 electron to it. So I'm going to go ahead and I'm going to say, well, according to the off-bow principle, they said that the electrons always occupy the lowest available space. So I'm going to put my little arrow in here. So there's my 1 arrow. And that would be, ladies and gentlemen, for the electron configuration, 1s, which is for my hydrogen atom. Okay? Now, let's go ahead and let's go to helium. Now, helium has 2 electrons in there. So, we're going to put element here, helium. Here's the element hydrogen. So, here's the element helium. And we have 2 electrons. So, we're going to have to go 1 arrow like this and 1 arrow down like this. Ooh, wait a minute. Well, why are the arrows going opposite of each other? It's that dude, Paulie. Yeah, Paulie. Paulie told us, he said that the arrows represent the electrons spinning opposite of each other. And you may remember in class I had you do this to simulate where the electrons are going. It's random. That's what Heisenberg told us. So this is what helium would look like. The 1s2, and that would represent 1s2. Yep, absolutely. Okay, now that we're going to move on, we're going to go on over here, and let's go do something a little bit more fun and exciting. Let's take a look at the periodic table, and I'm thinking, I am so interested in carbon. I am so interested in carbon. Carbon's going to be my friend right now. Okay, and we'll go here. So we're going to do carbon. Carbon has a big whopping 6 atoms. Okay, so we're going to have element of carbon. Carbon. So we know it's got 6 electrons. You'd say, how would you know this? Well, hey, I teach chemistry. That would be kind of scary if I didn't. But if you look up here on the periodic chart, you'll see a number 6. That's the atomic number. Well, remember, that's the number of protons in a carbon atom. That doesn't change. You change the number of protons, guess what? You changed its identity. Much like changing our DNA. Especially, you know, we talk about the XY chromosome and the XX chromosome pairs, you know, for humans. That would be a subject I'm not going to do a video on. But anyway, so we got 6 electrons here. If we got 6 protons, we can assume 6 electrons. So let's see, what would this look like? Well, it's going to look like this. It's going to look like, so we have, here's our carbon. We've got 6, so we're going to go 1, 2, 3, 4. Okay, so far so good. We're doing it. Now we have 2 more electrons. Now here, this is where we have to place it. Where do we place it? We'd have to go for 5 and 6, like this. Say, why couldn't you just simply put it over here with the arrow going upside down? Well, you have to put the arrow upside down to represent the opposite spins of the electrons. But here, you have to realize there is that off-bow rule, the lowest available energy orbitals. And this is the lowest. And you might want to think about the, I would call it the monopoly rule. When you play a game of Monopoly, you buy houses, you buy land, and then you buy houses to put on the land. If you got 3 lands of the same color, like the yellow, for example, you may buy houses and put them on the land. But if you have 3 lands and you buy 4 houses, you can't put 4 houses on 1 land. No, that has to be spread evenly. Just like the electrons here, they have to be spread evenly. I couldn't put the second electron here. I have to put it here. Okay, and that's carbon. And then I could go 1s2. Here's my electron orbital notation. 2s2, 2p2. And you notice I got 2 plus 2 plus 2, 6 electrons. Hey, not bad. Now, here's the kicker. How many valence electrons would carbon have? Here's the secret. You take the highest energy level that there is, and you count up the number of electrons. So in this case, 1, 2, 3, 4. Oh, wow, what do you know? Carbon has 4 valence electrons, and you guys might remember for electron dot diagrams, carbon has 4 valence electrons. That makes carbon pretty easy to go hook up with a bunch of other atoms out there. That is a real key thing for us. Okay, let's try another one. Let's pick another element. Let's go for neon here. Let's go for neon. Okay, we'll do neon. So here's our element. We're going to use neon. Neon has 10. Okay, 1, 2, 3, 4, 5, 6, 7. Notice I had to go all the way across because of that monopoly rule. 8, 9, 10. That's it. That's the whole thing right there. And guess what? How many electrons valence electrons does neon have? Remember valence? The outermost layer. Look at your highest energy level here. 1, 2, 3, 4, 5, 6, 7, 8. Oh snap! Neon is a noble gas. It doesn't react that easily because it's got the full outer layer of electrons. Yes. Neon's very happy. Now, what would the electron configuration look like for neon? Well, it's going to be 1s2, 2s2, 2p2. Oh, I'm sorry, 2p6. So, what's an easy way to count the number of electrons? 6 plus 2 is 8, plus 2 is 10. That's how you can actually proofread this, believe it or not. Yeah, can you imagine that? All right, let's go try find another one here. Let's go and look at another one. Let's take a look at, hey, here's sodium for 11. Okay, let's do sodium for 11, shall we? All right. So, in this case, my element is, okay, sodium. I'm going to have to write it a little bit slow. Now, we know that it's going to have already 10 of these, right? Because it's got 11 electrons. We checked that on the periodic table, right? Check to see the atomic number is 11. 11 protons, 11 electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Looks good. And notice how I'm going up the rows here. I went 1s, 1s2 to represent this, 2s2 to represent this, 2p6, yeah, and then 3s. Now, how many valence electrons does sodium have? 1, because the highest level it's got is 3. Oh my gosh. Oh snap. Yeah, so sodium has 11 electrons. It loses an electron. It now becomes positive, okay? Now remember, it wants to lose the electron because it's got its 8 underneath, see? Drop the electron, look, it's got its 8 underneath. Oh yeah. Good times, good times. All right, let's try for another one here. Let's try for a higher level one, okay? I am going to go ahead and I will put, let's go for chlorine here. Now I'm going to show you guys a shortcut. Absolutely show you guys a shortcut for this, okay? And here it is. Chlorine, we're going to use chlorine. Now chlorine has 17 electrons. We checked it out on the periodic chart. The atomic number is 17, okay? So here we go. 17. Now instead of going 1s2, 2s2, 2p6, that's just going to be kind of annoying. So why can't we turn around and say, hey, we know it's going to have 10 to begin with, and the 10 happens to match with the noble gas configuration of neon. Because neon's got 10, it's not going to go anywhere. Why can't we go and do an abbreviation for it? Wouldn't that just save us all the hassle of drawing these arrows up and down? Yes, yes, you can actually do this. And here's the secret. You draw a bracket like this. You put neon inside the bracket, so it's going to look. Okay. Yeah. I'm going to show you the secret. Uh-oh. It may not be liking me at the moment. In fact, I know it's not liking me. So we're going to have to, you know what, we're just going to have to go and put it over here. It's slow. It's lagging. Okay, we'll just work with it. So we have our bracket that looks like this, and you put the abbreviation in here. So I know I've got 10 in there, and I know it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Boom. How many do I have left? Well, 17 take away 10 leaves me 7. So that would mean I'll have to go 1, 2, because that's what the rules are, right? Opposite spins, 3, 4, 5, 6, 7. Notice I had to fill a Monopoly building, a Monopoly land, just like in Monopoly. So I had to fill in the 3 here, then go back and fill in the others until I had no more. Now, check this out. I have the whole thing of NE. Notice I didn't write any arrows here because I know this whole thing is neon. So I have 3s2, 3p5. So that is the correct electron configuration for the element chlorine. Oh my gosh, it's easy, isn't it? Once you get used to it. Now, how many valence electrons does chlorine have? We got to look at the highest energy level, which is 3. Count them up and weep. 1, 2, 3, 4, 5, 6, 7. 7 electrons. And what have I been telling my classes? 7 valence electrons for chlorine. Oh, snap. Another way that we prove that chlorine's got 7 valence electrons. Oh my goodness, I can't believe this. Okay, now at this point, I am going to need to do some erasing because I would like to do a bigger one with you guys if I can. All right, I realize that this thing is lagging, and maybe it's lagging possibly because I am sitting there and I am doing this. So let's take a look here. Let's see, which one would be more interesting and more fun to do? Okay, let's go. Oh, yeah. Let's go ahead. Let's do something really, really serious here. Let's go with strontium 38. Strontium 38, okay? Strontium has 38. The closest closest noble gas is krypton with 36. Okay, so here we go. Okay, so what are we going to do? Our element is going to be okay, starting to do that again. Okay, see, I tell you, I don't edit these. Fine, be that way. Okay, so you know that 36 is going to be for the krypton. Okay. It's kind of not cooperating. It's now cooperating less and less now. Okay. Okay, well, let's see. File, close, don't save. Okay. File, open, and let's get that orbital notation worksheet back. Oh, yes. Oh, yes. See, we're back. Back in action. Now, we talked about strontium. Strontium is SR. I see it's not working. Oh, there it is. SR. Okay, it's got 38 krypton, so it's going to have the bracket of krypton, okay, which is 36. Wow. So that means 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 20, 22, 24, 26, 28, 30, 32, 34, 36. Aha, here it is. I only need to put 2 arrows up here because I can do this. And how many valence electrons does strontium have? Oh snap, 2, because it's in the second column. How do I know this? It's right here, second column. Yeah, one last thing. Why is it that you're going 1s, 2s, 2p, 3s, 3p, then you got 4s before the 3d? Remember that Aufbau said you've got to fill the lowest available energy orbitals. 4s is at a lower energy level than 3d. Even though it's on a level 4, it's easier for the electrons to fill that. before it hits the 3D. That's why you're seeing the order that it's going in. Okay, hey, I hope this helped you guys.